Hello, fifth graders, and welcome to a read aloud of today's science ebook reading, that being this book here called Composition of Matter. Composition being a word that means what is it made of. So composition of matter means what is matter made out of. So when we take a close look at all the atoms and molecules that make up everything in our universe, we can see what they are made out of today. Now this ebook is part of today's science lesson, which is Unit 2, Lesson 9, called Particles of Matter. And a quick introduction to the book reads like this. What are the building blocks of matter? Let's read to find out. Read pages 4 to 17 in the ebook. Well, you heard the lesson, so let's go ahead and hop on in and take a look. Moving past the title page to the table of contents, we can see that pages 4 through 17 means we're only going to have to read about half the book today. So, table of contents, which tells you the chapters in the book and what page they start on. We can see that the chapters we'll be looking at today are called Through a Chemist's Eyes, Inside an Atom, Elements, and Molecules and Reactions. All things that may sound familiar if you've been following your science course closely so far. As for the rest of the book, you're free to read that on your own time if you wish, otherwise we may see it in a later science lesson. For today, let's go ahead and start off just with the required reading, starting here on page 4 with the chapter called Through a Chemist's Eyes. A chemist being a person who studies chemistry, which is the science of how matter interacts. So atoms and molecules, how they interact with one another and the world around them. Through a chemist's eyes. Look around you. What do you see? Maybe you see a book, a dog, or a tree. Maybe you're staring at your hands or your clothes. What do all of these things have in common? For one thing, they're all made of matter. Matter in and of itself is a pretty simple concept. In physics, matter is defined as anything that has mass and takes up space, or has mass and volume. But what does that mean exactly? Well, matter is everywhere. It is anything that can be touched, moved, or interacted with physically. Pretty much anything that can be described as stuff is matter. Trees and dogs are made of matter. You and this book are made of matter. Even the air around you is made of matter. Everything is made of matter, guys. But what else do people, trees, and air have in common? Well, they're all composed or made up of tiny microscopic pieces called atoms. Atoms, a key word this time. A-T-O-M-S, atoms. These atoms are unimaginably small, very, very tiny. In fact, there are more atoms in a single grain of sand than there are in the entire number of stars in the Milky Way galaxy. About 50,000 times more. That's an awful lot of little pieces. There is also a whole branch of science devoted to studying these tiny bits of matter, which, as we mentioned before, is called chemistry. Chemistry, the study of matter. Dive in and see the world through a chemist's eyes. So for a couple of captions here, we got this very famous scientist named John Dalton. He was the one who created what was called atomic theory, or the first to really start to imagine that the world was made up of tiny, indivisible particles called atoms. Now, the ancient Greeks really thought of this idea long before him, but he was the first to really make a proper scientific theory out of it. Furthermore, we got a blurb here about properties of matter. We've learned about properties of matter in some of our earlier lessons. Properties are how we recognize things, or the ways that we use to describe things. We know gold is a soft yellow metal. Soft, yellow, and metal are properties of gold. Size and mass are also properties. Anything you observe about a substance is a kind of property. So the fact that gold can be melted into molten gold is another of its properties. And for a little bit of a goofy laugh here, we got a little joke. Don't trust atoms. You know why? Why you shouldn't trust atoms? Because they make up everything. Oh, that's kind of silly, but I think it's kind of cute. So on that note, let's go ahead and move on now to page 6. Now looking at the next chapter called Inside an Atom. So what are we going to find inside of an atom, everybody? Let's take a look. The concept that everything is made of tiny pieces isn't new. Ancient Greek scientists believed everything was made up of tiny, indestructible balls. As it turns out, they weren't exactly right. The atoms we know today aren't ball-shaped, they're not solid, and they're not indestructible. In fact, atoms are made up of even smaller pieces, or particles, that being a word for pieces, called subatomic particles. Subatomic means that they are even smaller than atoms. And these particles include, and these three subatomic particles are going to be important to remember, folks, so pay close attention. These particles include protons, neutrons, and electrons. Protons, neutrons, and electrons. All atoms themselves are made up of these three types of smaller particles that we call subatomic particles. Let's take a look at what each one is. First, we're told protons and neutrons are both found in the center, or what's called the nucleus, of an atom. So if we zoom in on an atom there, you can see it's got that central mass in the middle. If we zoom in on that, we can see that that nucleus is made up of these two particles, the red ones being called protons, and the blue ones being called neutrons. So protons and neutrons have about the same mass, or about the same weight. Electrons are located outside of the nucleus. So if we look at that model of an atom right there, you can see how swirling around in these orbits around the outside are those smaller little particles right there. Those are the electrons. Electrons are located outside of the nucleus. Compared to protons and neutrons, electrons are tiny. The mass of an electron is about 1/2000th the mass of a proton or a neutron. So that means it would take about 2,000 electrons to equal the weight of one single proton or neutron. Because of this, the mass of the nucleus accounts for nearly the entire mass of the atom. But there is something else surprising about the way an atom is put together. The diameter of the nucleus is about 1/100,000th of that of an atom as a whole. That's right, the largest pieces take up the least amount of space. So for an interesting fact here, we can see we got a picture of looks like a football field here. And we're told that if an atom were enlarged to the size of a sports arena, like this one, its nucleus, the center mass where the protons and neutrons are, would only be around the size of a pea. A pea being the little vegetable that's like a little green ball. So imagine a tiny little pea at the very center of that football field there. That pea would be like the size of the nucleus of the atom, while the entire sports arena would be the size of all the rest of the atom, those big orbits where the electrons swirl around. So it's quite a big disparity there. One other little fun fact here, we're told the word atom comes from the Greek word atomos, which means indivisible, meaning it's not able to be broken down any further. Atoms are the smallest possible pieces of matter that we know of. Well, unless you get to what are called quarks, but that's a bit more advanced. We're not going to learn about those today. So continuing on, we're asked, how is this even possible? It's because of the way subatomic particles are arranged in the atom. Neutrons and protons are bound together very tightly in the nucleus. They are quite difficult to move or break apart. But electrons are always in motion. They buzz around the nucleus in a sort of field or cloud and are nearly impossible to track. So while the electrons themselves only account for a tiny portion of the atom, the field in which they are found makes up almost all of the atom's volume. Because of this, atoms are almost entirely empty space. That means, in turn, all matter is almost entirely empty space. Yeah, whoa, it's crazy to think about. Look at your hand. It seems solid enough, but on a microscopic level, it is made up almost entirely of empty space. Think of the biggest, heaviest, most solid thing you can imagine. That thing, whatever it is made almost entirely of empty space. It doesn't matter whether an object is heavy or light, big or small. If you could look at its atoms, you would find it is mostly made of nothing at all. It's quite a trip to think about, isn't it? The fact that an atom is made up of just that tiny little nucleus in the middle, which, like we said, only amounts to maybe about the size of a pea compared to a huge football stadium, and then those swirling orbits of electrons all around them. But if you think about what's between the nucleus of the atom and the electron orbits, there's really nothing in between them. It's just empty space. So pretty much all matter is empty space. It's very strange to think about, I know. Quick note about this man right here. We're told this is Ernest Rutherford, and he was known as the father of nuclear physics. In 1911, he presented a model of an atom in which the positive charges, those being the charges in the protons, were in the nucleus, and the negative charges orbited around the nucleus. The negative charges coming from the electrons. Bit about atomic power. We can use the power of the atom in order to generate lots of energy. And we're told here that a nucleus is very hard to split apart because of how tightly the neutrons and protons are bound together. Some split apart spontaneously, meaning on their own, while others split on impact with another particle. When this happens, energy is released. Scientists use this energy to create the atomic bomb. So, you may have seen footage of atomic bombs. Those are very, very large and devastating explosions that those bombs create. And it's pretty impressive to think that all that energy released in the form of a bomb really just comes from a tiny little atom being split apart. So we got, say, an atom of probably uranium here. It makes contact with another particle that basically breaks it apart. And as that atom is broken apart, that energy packed within it is released. And you can see when the energy is released, it's quite devastating for us. Oh, one other little fact here. We're told that atoms are 99.99999999999% empty space. If you know about your decimals, you probably recognize that that is very, very close to being entirely empty space, although technically not quite. Next part, opposites attract. Subatomic particles make up an atom, but these tiny pieces have another important role. They have electric charges. Electric charges. Electrons, those being these guys that swirl around the outside the nucleus in their orbits, have what's called a negative charge. Negative charge. That's why they appear in this picture as having a little minus sign on that. Minus means negative. Protons, on the other hand, have a positive charge, meaning, again, if you look at that model of the atom right there, the blue protons in there have a little plus sign on them. That means their electric charge is positive. While neutrons, as their name kind of implies, are neutral, meaning they have no charge at all, zero charge. They have no charge at all. They have no charge at all. Each charged particle interacts with other particles in certain ways. They work just like magnets, if you've played with magnets before. Since protons have a positive charge, they repel or push away other protons. Electrons also repel other electrons. But since protons and electrons have opposite charges, they are attracted to each other. Because neutrons do not have a charge, they neither attract nor repel other particles. The nucleus of an atom is made up of protons and neutrons, so the nucleus has a positive charge. Since electrons are negatively charged, they are attracted to the nucleus. This pole holds the electron cloud in place. So it's the fact that those negative electrons are attracted to the positively charged protons that allows them to continue to swirl around and around that positively charged nucleus without ever flying away. Even though they are not even close to the same size, electrons and protons have charges of equal strength. Atoms usually have a neutral overall charge. In order for this to be true, atoms must have an equal number of protons and electrons. So that's pretty important to note right there. Atoms like to have an equal number of protons in the nucleus, as well as an equal number of electrons swirling around the outside in order to keep those charges balanced. If you know how many protons an atom has, then you also know how many electrons it probably has. So a very strong force. So one question that's always kind of puzzled chemists is, why is it that if protons, which are positively charged, will want to repel or push apart from each other, then why doesn't the whole nucleus of an atom just completely fall apart when the protons just push away from each other and fly away? The truth is, we think we may have an answer for that question, which is described in this little box here. Why don't protons in the nucleus push away from one another, breaking the atom apart? Protons and neutrons are bound tightly together in the nucleus. The force holding them together is stronger than the force pushing them apart. Logically, this force is called the strong force, or the strong nuclear force. And that strong nuclear force is 1,038 times stronger than the force of gravity on Earth. So it's very, very strong. It's able to hold those positive particles together. Next section of the book is called Elements. Atoms can combine in a variety of ways. A substance composed of only one type of atom is called an element. For example, iron is an element. All of the atoms in pure iron are iron atoms. There are many types of elements, each with different properties. Some elements, such as mercury, are liquid at room temperature. mercury being a liquid that they used to use in old thermometers. Others, such as helium, are gases. Helium, what they use to fill up our birthday balloons. Still others are solids, such as lead. Some conduct electricity and heat, others do not. Elements can be many different colors. They can combine into different things. Some elements have a distinctive smell or taste. Regardless of these properties, you can tell each type of element apart by the number of protons it has. The number of protons it has. That means if you could add another proton to an atom, then it would be a different kind of atom altogether. Of course, doing that is quite difficult and requires a lot of energy. But the fact remains that what makes elements different are the number of protons. So as a couple examples, here we have ourselves a hydrogen atom, which its nucleus in the middle is made up of just one proton, and swirling around it is just one electron. So one proton balanced with one electron means that this atom is a hydrogen atom, element number 1. On the other hand, if we manage to get two protons together in the nucleus, 1, 2, which in turn is surrounded by two negatively charged electrons, 1, 2, the fact that this atom right here has two protons means that this is no longer an atom of hydrogen, it is now an atom of a completely different element called helium. That's the one we use to fill up our birthday balloons. And if you manage to get atoms with more protons, those are going to be atoms of different elements. Another example is this one. We have here a picture of a bit of info lifted from the periodic table of elements. We have a name of an element called aluminum, and we're shown right here that its atomic number is 13. What that tells us is that if we zoom in onto the atom of aluminum, we would see that it actually has 13 protons packed into its nucleus in the middle, and it would have 13 electrons swirling around in its shells on the outside. So for a little bit more info about elements, we can take a look here. We're told shortening it up. The names of elements can get quite long and are not always fun to write over and over again, like aluminum, for example. No one wants to keep writing the word aluminum, so scientists use standard abbreviations or chemical symbols for each type of element. The symbols are 1 to 3 letters long, with the first letter always capitalized. They are usually composed of letters from the element's English or Latin name. So in this case, the element name aluminum is often shortened to just Al. Makes it a little easier to write. Oh, and similarly, hydrogen is often shortened to just the letter H, and helium is shortened to just the letters He. So every element has its own special abbreviation or shortened name like that. Continuing on. Useful elements. When you go to a water park or swim in a pool, you'll probably notice that the water has a very strong odor or strong smell. You're smelling chlorine. Chlorine is a useful element that is commonly used as a disinfectant, meaning it kills germs and bacteria. Pouring the right amount of chlorine in pool water will keep the water clean. Chlorine is also used in bleach to keep clothes and dirty toilets clean. I guess one other fun fact there, the longest English word is the name of the chemical that has 189,819 letters. Wow, okay. I don't know what chemical that is, but it sounds pretty wild. I'll have to look that up one day. Next up, we're told about electron shells. Now, you may remember we were talking about those orbits, or those kind of circles that electrons would swirl around the outside of the nucleus of an atom. Turns out that those orbits can be treated as shells. So what are electron shells, everybody? Electrons don't just buzz around randomly. They occupy different energy levels or shells of an atom. A certain number of electrons fits into each shell. When one shell is filled, electrons start filling up the next shell. A full shell is very stable and wants to stay the way they is, but an incomplete shell is not stable at all. The shells want to either be full or empty. The outermost shell is called the valence shell. So in this model of this atom right here, that shell on the outside that contains all those electrons right there would be called the valence shell of this electron. Protons and neutrons don't change much in their compact nucleus, but electrons can easily jump from atom to atom. When the valence shell of an atom is not full, the atom tries to become full. It may do this by giving its electrons away to other nearby atoms, or it may take electrons from other atoms. They may also share electrons with neighboring atoms. So atoms might give or take or even share their electrons in order for their shells to be balanced or full. The number of valence electrons in an atom controls how reactive an element is. The number also determines the type of elements it will react with and how they will react. This means that how an atom acts is based almost entirely on the number of valence electrons it has. So that valence electron shell is very important. So a couple fun facts here. The element francium, discovered in the country of France, is the most unstable naturally occurring element. Its 5th, 6th, and 7th shells are not full. So an atom of francium is probably going to want to swap its electrons with a lot of other atoms out there if it can help it. I think explaining this page would take a little while, so if you're feeling savvy, feel free to take a look at this diagram called Filling the Shells. But for the sake of time for our ebook reading, let's go and continue. Alrighty. Final chapter, Molecules and Reactions. Elements that have an incomplete valence shell are very reactive. But what does that mean? When atoms react with one or more other atoms, When atoms react with one or more other atoms, they join together. A set of joined atoms is called a molecule. Very important word as well, molecule. A molecule can be made of the same kind of atoms, making it an element, or it can be made of different kinds of atoms, making it a compound. A compound often has very different properties from the elements that made it. For example, pure water is a compound. It is made of hydrogen, which is a gas, and oxygen, which is another type of gas. So it's interesting that these two elements, hydrogen and oxygen, which are both gases, when they combine, or when hydrogen and oxygen atoms combine together to form water molecules, they actually form a liquid water. When two hydrogen atoms and one oxygen atom come together with enough energy, they combine to form a water molecule. Hydrogen and oxygen are both colorless gases at room temperature, but as you know, water is a liquid at room temperature. Like I said, oxygen won't turn to liquid until it reaches a chilly negative 219 degrees Celsius, or negative 362 degrees Fahrenheit. Very, very cold. And hydrogen doesn't turn into liquid either until it reaches 259 degrees Celsius, or 443 degrees Fahrenheit. Imagine if it were cold enough to have liquid oxygen raining out of the sky. That would be incredibly cold. There are millions of compounds known today, and more are always being discovered. Not all atoms can react with one another, though. It all comes down, once again, to the arrangement of their electron shells, like we saw previously. So while all compounds are molecules, not all molecules are compounds. And you'll find it that elements and compounds that are very unstable tends to be the ones that react the most, or that react the most severely when mixed with other ones. So some atoms are so reactive that they are not found in their pure states in nature. Just how reactive are we talking here? Sodium is a very reactive element. It will react with oxygen in the air. Sodium also reacts with water, and if the temperature is right, it can actually catch fire. So I think that's a picture right there of some sodium being dropped into some water at high temperature. It actually causes it to explode and catch fire. So sodium is quite reactive. Now a bit about another super scientist. Marie Curie was a Polish scientist who studied matter. That's her right there. She and her husband Pierre discovered two elements called radium and polonium. Pierre and Mary won a Nobel Prize in physics in 1903. In 1911, Mary won a second Nobel Prize. Only 4 people have won this prize twice. So Marie Curie was a very brilliant chemist. We discovered a lot from her. Alright, I think this may be the last 2 pages here. Yes. Alright, so let's go and finish these 2 up. Next up, types of bonds. So how do different atoms bond with each other, or fuse together to create molecules? In order for 2 or more atoms to bond or join together, they must physically meet. They must also be compatible. This means they have the right properties to create a reaction. In addition, they need energy to form the bond. If these requirements are not met, then no reaction will occur. Atoms want, quote unquote, to be as stable as possible. Unstable atoms usually bond in an attempt to complete their valence shells. There are different ways that 2 or more atoms can bond. One way is through a covalent bond. covalent bond. Covalent bonds form when two of the same or similar atoms share electrons between them. To do this, they join valence shells. A covalent bond is usually formed between two nonmetals. Some elements, such as hydrogen, will form covalent bonds with themselves. They do this if there are no other elements to react with. These elements are called diatomic. Diatom means two atoms. Di meaning two, and then combined with the word atom. Diatom, two atoms. These atoms are naturally found in sets of two. Hydrogen, oxygen, fluorine, and chlorine are all examples of diatomic elements. So first, doubling up, we're told atoms can create what's called a double bond. A double bond is when two atoms bond with each other twice. When two atoms are missing two electrons, they can fill each of those missing spots and create two bonds. Carbon is the most common element to form this type of bond. So you can see there are two, well, these appear to be two hydrogen atoms, because they have just the one proton and the one electron. But you can see the way that they've bonded together like that, sharing their electrons. Similarly, we're told, no fair, atoms don't always play nicely. If atoms have different charges, then they might share their electrons unequally. One atom might hog the electron. Oxygen tends to hog electrons, giving it a negative charge. When hydrogen bonds with oxygen, the positive and negative charges attract, forming water. So there we go. We once again have two oxygen atoms there. Oxygen being element number 8, which means it has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And then the same for this one here. However, the outside shell of an oxygen atom only has 6 electrons. 1, 2, 3, 4, 5, 6 for this one, and then 1, 2, 3, 4, 5, 6 for this one. And so, what these two oxygen atoms are doing is they are sharing some of their electrons so that they both end up with 8, because they want to be able to have 8 electrons in their outer valence shell. Alright, and lastly, we have another kind of bond is what's called an ionic bond. An ionic bond forms between different types of atoms. In fact, ionic bonds usually form between metals and nonmetals. An ionic bond is formed when one or more atoms take electrons from another atom to fill their valence shells. This charge creates charged ions. Ions, those being atoms with an electric charge, because the number of electrons and proteins in each atom do not match. For example, sodium has 1 electron in its valence shell. Chlorine has 7 electrons in its valence shell. The sodium wants to give up an electron, right? So that it can have none in its outside shell. And chlorine wants to gain one to fill its outer shell. So the electron from sodium jumps over and fills the chlorine shell. Now, the sodium has a positive charge because it has more protons than electrons. And chlorine now has a negative charge because it has more electrons than protons. These two atoms are called ions because they have a charge. Since opposites attract and ions come together and form an ionic bond. This forms a new molecule called sodium chloride, also known as table salt. So ordinary table salt, everybody, the kind that you sprinkle on your food to give it some flavor. Pure sodium is a very silvery metal that is soft enough to cut with your ruler. Oh, but don't get it wet. It pops and fizzles when it touches water, like that. I think we saw that earlier, right? Chlorine is a poisonous green gas, but put them together and you have table salt. Again, very interesting example of two completely different elements when bonded together to form a molecule end up creating something very different, in this case table salt. Now once again, metals versus non-metals, this is a handy chart if you want to read it on your own, but for the sake of time, I think I'm going to go ahead and skip reading that for us in our read aloud today. So at this time, I will say thank you so much for joining us. Hopefully this gave you some insight into what matter is made of, what atoms are, what elements are, how they combine together to form molecules, and the different types of bonds that can exist between different types of atoms, like ionic bonds, covalent bonds, and the like. So take care, everyone. Keep working hard on your science, and I will see you again for the next Read Aloud. Take care and have a good day. Goodbye.